We are Group 9 and our topic was the failing of steel reinforcement in concrete. Steel reinforced concrete has long been the cornerstone of modern infrastructure, a material marriage that leverages concrete's formidable compressive strength with the tensile resilience of steel. It's affordable, widely available, and easy to work with, but despite more than a century of use, one fundamental flaw remains. Steel corrodes, and when it does, it doesn't just weaken, it expands. That expansion exerts internal stresses on the surrounding concrete, leading to cracking, spalling, and ultimately structural failure. In engineering terms, it's not just a material flaw, it's a systematic design vulnerability. This isn't theoretical concern. We've seen it in the Florida Keys and in the Boston's Big Dig. These failures are not isolated, they're endemic, and the cost isn't just financial. Every crack is a compromise, every repair is a risk, every failure is a warning. In response to this challenge, several alternative reinforcement structures were investigated, including stainless steel, basalt fiber polymers, geopolymer concrete, and carbon concrete. After a critical comparison of the material properties, durability, environmental impact, and life cycle cost, carbon concrete was selected as the focus of the study. This investigation aims to assess the performance limitations of steel reinforced concrete by analyzing common failure mechanisms using principles of material science and engineering. The project will evaluate mechanical properties, durability, cost, and environmental impact of current and alternative systems. The redesigned solution must offer improved resistance to corrosion and long-term environmental degradation, while maintaining or exceeding the structural integrity of conventional reinforcement concrete. It should lower the embodied carbon, extend service life, and reduce maintenance requirements. Furthermore, the proposed system must be cost-effective over its full life cycle and compatible with current emerging construction methods. By adopting a material-driven redesign strategy, this project aims to improve the reliability, sustainability, and long-term economic viability of reinforced concrete systems operating in aggressive environmental conditions.
Basalt fiber reinforced polymer rods have been engineered as a concrete reinforcement to replace steel due to steel's highly corrosive nature. To protect the steel, extra concrete is poured to ensure air and water doesn't interact with it. However, this can become expensive and isn't environmentally friendly. Basalt fibers are made from basalt rock, which is a type of volcanic rock formed when lava cools. These fibers are combined with polymer matrix composites to reinforce the fibers. Basalt volcanic rocks are natural and plentiful, therefore basalt fibers are relatively inexpensive to manufacture and are environmentally friendly. The basalt rods are non-corrosive. This solves the issues related with steel-reinforced concrete, such as cracking due to rust expansion and excess concrete being poured. However, there are drawbacks when considering basalt rods as a solution to concrete reinforcement. One of the disadvantages is that as the number of rods increases, the number of spaces in the concrete increases too, leaving room for water to collect. When the water freezes, the water expands, causing cracks to form in the concrete. All the disadvantages must be considered before replacing steel reinforcement in concrete with basalt fiber reinforced polymer rods.
Geopolymer concrete is a promising alternative to regular concrete that replaces typical concrete with aluminosilicate-rich industrial byproducts such as fly ash or ground-granulated blast furnace slag. Traditional concrete makes use of Portland cement, which contributes to the rising CO2 emissions. It is susceptible to cracking due to shrinking of the material during the curing process. It has an extremely low tensile strength of just 15% of its compressive strength, and it makes use of steel reinforcements, which degrade very easily. Geopolymer concrete addresses these issues. The manufacturing process produces 80% less carbon dioxide. Polymer reinforcements are less affected by humidity and acidity. The minimal shrinkage during curing allows for a stronger, more versatile structure. And the concrete itself has little tensile strength, but the addition of simple carbon polymer can increase the tensile strength by up to 28%. As per its limitations, geopolymer concrete is manufactured using substances which are classed as both hazardous and caustic. Additionally, there are no global standards to determine how the substance should be mixed, and many geopolymer substances require elevated and exact temperatures which are not achievable in nature. Unfortunately, geopolymer concrete is not a valid solution in this case due to the negative cost and manufacturing implications. Additionally, there is not enough data to back the durability regarding this product.
While steel is primarily used to reinforce concrete, it has some severe drawbacks, like its susceptibility to corrosion and its high density. Carbon concrete seeks to not only succeed where steel reinforcements fail, but to surpass them and open up new avenues for what is possible in construction and civil engineering. When talking about carbon concrete, what is really meant is a fine concrete mix reinforced with carbon fiber structures. These structures are made from carbon fiber reinforced composite polymers, which are then shaped into two main support structures for carbon concrete, traditional rebar and carbon fiber meshing. The CFRP reinforcements are traditionally made from a synthetic polymer called polyacrylonitrile, or PAN, which is then placed within a high temperature environment to rearrange the carbon structures to get traditional carbon fiber. As one can imagine, this is an expensive process, but the production of carbon fibers is being dramatically changed with the introduction of lignin, an organic carbon polymer chain used to provide rigidity to cell walls within trees. Lignin is very readily available as it is one of the most common byproducts when it comes to the paper pulping process. Why use carbon fiber? To understand why carbon fiber is a strong alternative to steel reinforcement, we need to compare their performances. Steel needs to be encased to prolong the time before corrosion sets in, and also needs more concrete to support its weight. On the other hand, carbon fiber doesn't corrode, is a fifth as dense, and has a tensile strength of around 5.7 gigapascals, over 5 times that of steel's 1.1 gigapascals. This allows for lighter designs using less material overall. Carbon fiber reinforced concrete is still in the early stages of development, but with its production becoming more and more cost efficient, combined with its amazing physical properties, carbon fiber is rapidly becoming the best solution for concrete reinforcement.
One of the main issues with implementing CFRC worldwide is the lack of standardization. This in turn makes the construction process harder and more labor-intensive, thus an increase in labor costs. With that being said, more care for both the manufacturing and installation of CFRC is essential. If done poorly, this can lead to the material and subsequently the structure to fail. An example of this failure could be in carbon fiber cement matrix bonding. When the surface of carbon fiber is smooth, it can lead to poor bonding with the cement matrix and thus leads to cracks forming, which allows for crack propagation to take place. Also, poor bonding can lead to poor stress transfers between the layers. It is important that safety measures are taken place when processing carbon fibers because they release fine fibers and dust. These dusts can be hazardous and also cause skin irritation. Carbon fibers can be recycled by means of grinding, though it can be challenging since fibers are strong. Figure 2 shows how carbon fibers can be recycled and reused. Another application of this recycled carbon fiber is in concrete. The recycled carbon fiber increases fracture toughness of the cement. By using recycled carbon fibers, it is reducing waste, which is good, since carbon fiber is not biodegradable. As seen in Figure 3, steel waste makes up a big portion of construction waste, and by using this recyclable carbon fiber, we can greatly reduce this percentage. CFRC has a bright future if standardizations are made and for companies to pay the extra labor and manufacturing costs upfront, since CFRC requires less maintenance in the long run compared to steel.